All right, welcome ladies and gentlemen. This purpose of today's lecture is to move further into our discussions of radioactive behavior and look at the idea of half-life, a topic which you covered earlier in your science careers here at Ralston Valley in earth science. So let's go ahead and get started. As we had been discussing, radioactive decay is the process by which radioactive isotopes undergo the spontaneous emission of particles due to their instability. And remember that word spontaneous implied to us that the process of radioactive decay was inherently unpredictable. There was a degree of randomness to it. And in order to describe, therefore, the amount of time it takes for a sample of radioactive material to decay, we can't definitively define when all the particles are going to break apart because, again, that process is a spontaneous process. It is a random process. So if you're sitting around waiting for an atom to decay, it could take 5 seconds, it could take 100 million years. You never really know. And as such, determining the total amount of time it takes for a sample of radioactive particles to decay is an impossible task. You never know when all will decay because the process is random. Now that being said, we still won't have a measurement of the amount of time it takes us radioactive particle decay, because that indicates to us the relative stability of how essentially stable a radioactive nucleus actually is. The longer it takes it to decay, the more stable that nucleus is. The shorter it takes to decay, the more unstable. And as such, what we use to describe how long it takes to decay is not the total time, since that's inherently unknowable, but what we call a half-life. A half-life is, by definition, the amount of time it takes for half of a radioactive sample to undergo a nuclear decay. Now, even though we can't say how long it will take for all the sample to decay, because any one individual particle decaying could take literally hundreds of millions of years or a fraction of a second, we can say, on average, how long it takes for half of the sample to decay, since this is essentially a mean value taking into account the average amount of time it takes these particles to decay from a much larger sample. And if you take a look on your periodic tables, you'll notice that there is, in fact, a table of selected radioactive isotopes in the upper table and the above. If you take a look at your periodic tables, you'll find out that there is a table of selected radioactive isotopes up above the main table itself there, which lists half-life times. For example, if you take a look on the right-hand column at the element uranium, that's atomic number 92, you'll find that there are a number of different isotopes of uranium listed on there. And looking down to the most abundant of those radioactive isotopes of uranium, you'll find uranium-238. Immediately after that 238 is a number there, which is 4.46 times 10 to the 9 Y. That is the half-life of uranium. That is 4.46 times 10 to the 9th years, 4.46 billion years. So if you have a sample of 1 gram of uranium-238, after about 4.5 billion years or so, the half-life time of that uranium, you'd have half of the sample left. That's half a gram would remain. The other half would have decayed. And if you look up a couple above there, you'll find another radioactive isotope of uranium, which is uranium-235. You'll see for uranium-235, the half-life time is listed as 7.04 times 10 to the 8th years. Now that is a significantly shorter amount of time, which implies the rate at which uranium-235 decays is faster. So the shorter the half-life, the faster the rate of the decay, the more unstable the nucleus. So, with that general definition of half-life taken care of, let's now take a look at the map behind how we can deal with half-life problems. In general, within a half-life problem, we have 5 different variables we can deal with. They're listed up here on the board for you. They are, number 1, the total amount of time which has gone by. We indicate that in their equations with the variable t subtotal. Number 2, we have the amount of time of 1 half-life, labeled in your equations as t1 half times 1 half-life. Number 3, we have the number of half-lives that have gone by. That gets a little lowercase n for number. And then 4 and 5 are all about the amount of the substance that we have. The initial amount that we start with, we label n sub I, or the number of particles initially, and the final amount being number of particles n sub f. Now, taken together, those are the 5 variables that we can use to describe a radioactive system in terms of its half-life. In general, in most of the problems you'll be dealing with in class, the variable you have to pay most attention to, the kind of keystone to all of these problems, is variable number 3 here. That is the number of half-lives that have gone by. So again, most of our problems we solve will be looking for that number n, at least in part, to solving the problem. So, given those 5 different variables here, let's take a look at a couple of different approaches for solving a half-life problem. The first approach we're going to use here is what we refer to as the chart method. This is a method by which we're kind of just going to use logic and the definition of a radioactive decay half-life in order to get to a final answer. So let's take a look at how we can solve this. Our problem states that the half-life of californium-251 is 900 years. And a sample of that metal currently has a mass of 10.0 grams. The question we want you to answer for us is, what mass of californium-251 will remain after 4,500 years has gone by? So, with this setup here, just like you've been trained in previous science classes, physics in particular, the very first thing we want you to do is to go through and identify your variables in this equation. So to begin with here, taking a look at the numbers here, we have a variable here which is 900 years. And that's given to us as the time of one half-life. From our discussion earlier, we said that we will label this variable as a half-life time. Let's label it as T1 half. Next, we've got a sample of metal which currently has a mass of 10 grams. That mass of 10 grams is the initial mass of the sample. So let's label this as our variable n sub I, the initial amount. And then the final piece of information it gives us in the problem is it asks us what mass will remain after 4,500 years has gone by. So this is the total amount of time which has gone by, so let's label this as T total. So we've got 3 variables in our problem, that is 900 years, 10 grams, and 4,500 years. And what we're looking for in the end is the mass of californium that remains. That would be the final amount, and so that's what we're looking to try and find in the end. Now the first approach I'm going to take to solving this problem is what we refer to as the chart method. In the chart method, we're essentially going to look at how much of the sample remains after each half-life has gone by. And to do that, we're going to go ahead and set up a simple, what we call a T-chart here. And in this T-chart, on the left-hand side, we're going to have n, that is the number of half-lives that have gone by. And on the right-hand side of the chart, we're going to have n sub f, that is the final amount remaining after that number of half-lives has gone by. Now, in terms of how we solve this, the key, as I mentioned earlier, to solving most of these problems is to figure out how many half-lives have actually gone by. And we've got an easy place to start there. Given that we have been given both the total amount of time and the time of one half-life, if 4,500 years have gone by and each half-life is 900 years, to find n, the number of half-lives, I could simply take the total time and divide it by the time of each half-life, which in our problem would again be 4,500 years divided by the time of each half-life of 900 years. And that gives me a number of half-lives here, which is 5 half-lives. So 5 half-lives have gone by. Into my T-chart, I'm going to go ahead and put 0, 1, 2, 3, 4, and 5, showing the number of half-lives that we expect to occur over the course of time. And on the right-hand side, I'm going to work through and figure out how much remains after each half-life. Now, we've got an easy place to start here. After 0 half-lives have gone by, none of it will have decayed. And as such, we'll have the entire sample present. We were given an initial amount of 10.0 grams, so we'll go ahead and label that. After 0 half-lives have gone by, we have a mass of 10 grams. And from this point on, we're just going to go ahead and apply our definition of half-life. By definition of half-life, the amount that remains after each half-life is half of what you started with. So after one half-life, if we start with 10 grams, we'd be down to 5 grams. And then after another half-life passes, we would have half of the half that remains. So starting with 5 grams, we would now, after 2 half-lives, end up at 2.5 grams. And then you can see where this process just continues here. After 3 half-lives, we'd have half of what remains again, which would be 1.25 grams. After 4 half-lives, we'd be down to 0.625 grams. And then last but not least, after 5 half-lives, we have 0.03125 grams. And that brings us to our final answer there. Now please do be careful here. You'll see that we seem to be growing our number of significant figures as we go here. So we need to make sure we do pay attention to sig figs in this problem. Looking at the given values in our problem, 10 grams had 3 significant figures present in it, as those zeros are significant zeros. However, the number 900 years, the half-life of Californium-251, is only good to 1 significant figure right there, which implies we can only answer our problem to 1 sig fig, which would give me a final value of 0.3 grams of our radioactive Californium-251 remaining after 4,500 years has gone by. So, that's essentially the chart method. Find the number of half-lives that have gone by, and then start with the initial amount and just divide by 2 each time you go through a successive half-life. Now there are some limitations to this chart method. You'll notice that there's really no way we can deal with this chart method if we have an amount of time that's gone by which is not a whole number of half-lives. And as such, we need another approach that is a more mathematical approach in order to go through and solve this problem if we had a non-whole number of half-lives that have gone by. So in order to derive an equation that will get us to that point, what I want to do here is I want to take a look at how we actually got down to that final value of 0.3125 grams in this problem. Essentially what I've done is I started with the initial amount, that was n sub I, the 10 grams, and I multiplied it by 1/2, a total of 5 times, where 5 was the number of half-lives. Now mathematically speaking, multiplying by 1/2 5 times is equivalent to 1/2 to the 5th power. So essentially to get down to that final amount, n sub f, I took the initial amount and multiplied it by 1/2 to the 5th power, where 5 was equivalent to the number of half-lives, n. So this essentially gives you here now a mathematical equation that we can use, rather than using the simple chart method, to go through and calculate a final amount. That is, you take the initial amount and multiply it by 1/2 to the n power. And you'll notice here that there is nothing in this equation that says n must be a whole number of half-lives. Which means if you have a fractional number of half-lives that have actually gone by, the equation will work, whereas the chart method will not. So this equation is your most important equation for dealing with half-lives. Final amount, n sub f, is equal to the initial amount, n sub I, times 1/2 to the n, where n is the number of half-lives. And you'll see that we'll get to the same equivalent answer, that is the initial amount we started with of 10.0 grams, times 1/2 to the 5th power gets us 0.3125 grams, same value which we got when we used the chart method. So, here's your main equation. Now that we've derived that main equation, take a look next at a couple of other things that we can deal with in terms of making these calculations. The key to solving these problems, as I mentioned in the last problem, is generally finding the number of half-lives n. In the last problem, we found the number of half-lives that have gone by taking the total amount of time and dividing by the time of 1/2. But let's say instead of having the total time and the half-life time, instead let's say you had information about the initial and final amounts and no information about the time. This is probably a more likely real-world scenario. Very rarely do you know the total amount of time which has gone by. More often than not, you'll be using these problems to determine the total amount of time, much like you did in earth science with your radioactive decay calculations for, say, carbon dating. So in this type of problem then, you're more likely to have information about the initial and final amounts of the radioactive material in the sample. And we're going to use those in order to solve for the number of half-lives that have gone by. Now the trick is this. From our half-life equation, looking at that half-life equation, the number n of half-lives that has gone by is up here in the exponent. And if I want to solve for that value n out of the exponent in terms of both initial and final amounts, I need to get that number n out of the exponent, which means I need to inverse that operation. And you guys are probably having some mathematical fears right now because you recognize from your math days that the inverse operation of an exponent is a logarithm. Now, happily for you, we are going to go ahead and do that math for you here. What I've done is I've taken the log of both sides of this equation and then applied some of our log rules and rearranged the equation into a new version of the equation, which is kind of easier to use, to solve for that value n. And that equation is right down here, where n, the number of half-lives that have gone by, is equal to the log base 10 of the initial amount divided by the final amount, ni over nf, divided by the log base 10 of 2. So using one of these three equations here, you should be able to get yourself to any answer of a half-life problem which we're going to ask you in the course of this class. So, with those equations taken care of, let's next go ahead and do a second example problem. For our second example problem here, we've got a sample which originally contained 0.0500 grams of radioactive iodine-125, and the half-life of that iodine-125 is 60.1 days. And the question that we're going to ask you here is how much would be left after 88.5 days has gone by. So, again, just like before, let's start by identifying our variables. 0.0500 grams is the initial amount of the sample we started with. We're going to go ahead and label that as n sub I for our initial amount. The half-life given to us here is 60.1 days. Let's label that as T 1/2, time of 1 half-life. And last but not least here, how much is left after 88.5 days has gone by. That's the total amount of time which is left, so let's label that as T sub total. So given these three variables that we have right here, let's go ahead and take a look back up at our equations and see where we can get to the end. We want to know how much is left, which means we're looking for the final amount, n sub f. In order to get to the final amount in our equations, we need to know the number of half-lives n. So looking at the data which we've been provided here, we have both the total amount of time which has gone by and the half-life time, which means the equation we want to use here is this one right here to solve for the number of half-lives n that have gone by. So let's start with that first. The number of half-lives n is equal to the total time divided by the half-life time, which in this problem would be 88.5 days divided by the time of 1 half-life of 60.1 days. And if we do a quick calculation, 88.5 divided by 60.1 gives us a number of half-lives that comes out to be 1.47 half-lives. Now that we have the number of half-lives that have gone by, we can simply apply our half-life equation to solve for the final amount, where n sub f, our final amount, is equal to the initial amount we started with, n sub I, times 1/2 to the n power, where n is the number of half-lives, and plug in our variables. We started with initially 0.0500 grams. We're going to multiply that by 1/2 to be 1.47 power, the number of half-lives. And plugging that in gives us a final answer of 0.018 grams of our radioactive sample remaining. And I apologize there, guys, that should have been to one more sig fig. Let's go ahead and give that at 0.0180 grams. Stop for a moment to think if that answer makes logical sense. You see that we started with 0.0500 grams. After 1 half-life, we would have half of that remains, which would be 0.025. After 2 half-lives, we would have 0.0125. So our answer lies somewhere between how much we would have after 1 and how much we would have after 2 half-lives, which sounds like then this answer seems like it's right about what it should be. And again, this is a problem that could not be solved using the chart method because our number of half-lives that went by were not a whole number. So that's essentially it, and that wraps up our discussion of half-lives.